Okay, so let's try to understand the problem 01 knapsack. I mean, it is one of the famous and important problem to do many problems actually. So, I mean, if we understand this problem, we can solve many problems. Okay, so the problem say that so there is a thief or a backpacker. So he has a bag of capacity W. Okay, and what he so he is trying to pack items. Okay, so pack items list is given, their weight is given. So basically weight is given. So let's say 1 2 4 5, and for this, okay, so for this there is a value also assigned, or cost also, or profit also assigned to this. So basically 5 4 8 6. Okay, so if he picks 1, so he will get a profit of 5. If he gets 2, he will get a profit of 4. If he gets 4, he will get a profit of 8. If he gets 5, he will get a profit of 6. Okay, so now the problem say that we need to find the maximum profit he can gain, okay, or he can get. So basically we need to find the maximum profit, okay, with this capacity. So capacity is fixed. Now with this finite capacity, we need to find out like what is the maximum value or profit we can make, okay, or the thief can make, or the backpacker can pack items. Okay, so I mean, looking at the problem, it almost looks like a optimizer problem, because we need to find the maximum profit or maximum value over here. Now whenever we have like optimization problems, which algorithms comes to our mind? So either we can go with greedy, or we can go with dynamic programming. Okay, so if we go with greedy, right? So let's check that whether we can proceed with greedy or not. Okay, by taking the same example over here, what we have taken 1 2 4 5. Okay, and capacity has been given as 5. Okay, and this is weight array, and value has been given as 5 4 8 6. Okay, now okay, so I'm greedy, right? So what I will do, I will pick up the most valuable items first. Okay, so I will take 8, which is corresponding to 4. So I will take weight 4. Okay, so now if I take weight 4, okay, so what will be the remaining weight for me? So remaining would be 1. Okay, so now the remaining would be 1, and value I gained or profit I gained would be 8. Okay, now remaining would be 1. Now with remaining 1 capacity, okay, so what we can do, like I can only take 5, which is of weight 1. Okay, so if I take weight 1, then remaining would be 0. And value I can get is 5. Okay, so now total value gained over here would be 13, or it will be the total profit will be 13. Okay, so expected answer also 13. Okay, now this is fine. Okay, so I mean, we can proceed with greedy. Okay, now let's take another example. So let's take weight has been given as, so this is example 1. Okay, and this is example 2. Okay, so over here weight has been given as 537. Okay, and profit has been, or value has been given as 40 60 80. Okay, now again I am greedy. What I'll do, I'll pick up this, and and the capacity has been given as 8. Okay, capacity 8. Okay, now over here I'm greedy. So what I'll do, I'll make locally optimal choices. Okay, so at each step, so if I make locally optimal choices at each step, then 80 will be the most valuable item. Okay, so I'll pick 80. So value would be 80. Weight I have taken as 7. Remaining would be what? 8 minus 7 would be 1. Okay. Now can I pick any other items? No, because I have capacity, remaining capacity is 1 only, because then I cannot take any other items, right, over here. Then but if I am a little intelligent, like if I have little brain, then what I can do, like I can take 5 and 3. So 5 and 3 would be having 40 and 60. So 40 plus 60 would be 100, and this is the maximum profit I can gain. Okay, so you can see over here, like greedy fails over here because greedy did not give us the desired result over here. So greedy fails over here. So we cannot pick greedy to solve this problem. So we cannot pick greedy. So what we can do, we have to pick dynamic programming only. Okay, so basically what we have to do, we have to pick we have to generate all the possible combinations. Okay, so first generate all possible combinations, and when we are generate all, then we can think of with help of recursion. Okay, and whenever we have combinations, that we can think of backtracking. Okay, so with the help of with the help of recursion, so we can make all possible combinations, and we should make like the possible combination should be like I will pick an item, like I will pick an item from over here, I will pick an item over here, so that should be lesser than equal to capacity. So I will not pick any item like my total weight should be within the capacity. It should not be like above capacity, because I have a finite weight. Okay, or a bag cannot be increased, like it's not responsive, right? I mean we cannot increase, right? So now the second case becomes to get the maximum from all possible combinations. From all possible combinations. Okay, so let's take an example over here. Okay, so 1 1 1. So weight has been given as 1 1 1. Capacity is 2, and value array has been given as 10 20 30. Okay, so we'll start with F32 because we are having 3 items over here. Okay, so 2 is the capacity. Okay, now if we include the third item, then we'll go for the second item. Okay, and remaining weight will be 1. If we exclude the third item, then what will go? We'll go for the second item and remaining weight remains same. If we include the second item, then we'll go for first item and remaining weight would be 0. If we exclude the first item, then second item, then what will go? We'll go for first item and the remaining weight would be 1. Okay. If we include the first item, then we'll go for then we are out of item, so it will be 0 and remaining weight will be 0. If we exclude the first item, then we'll go for 0 and 1. The remaining weight will be remain same. Okay. Now on the right, so if we include the second item, then what will be? It will be f of, we'll go for the first item and the remaining weight will be 1. If we exclude the second item, then it will be f of 1 comma 2. Remaining weight remains same. If we include the first item, then what will be our case? It will be, we'll go for the 0th item, but it is currently we have already included first item, so it is out of item, and the remaining weight will be 0. Okay, and if we exclude the first item, then we'll go for 0 and remaining weight remains same. For this we'll include the first item. Okay, we'll include the first item, and then it will be 0 and remaining it will be 1. And if we exclude the first item, then what will happen? So it will be f of 0 2. Okay, now let's take a different color. So when we had included the third item, then it added 30. Okay, and when we excluded third item, so it added 0. Okay, when we included the second item, so it added 20. Okay, when you excluded the second item, it added 0. When you included the first item, it added 10. Okay, and when you excluded first item, then it included 0 over here. Similarly over here, when you include the second item, it added 20. When you exclude the second item, it added 0. When you included the first item, then it added 10. When we excluded it, so it added 0 over here. When included over here first item, then added 10, and when excluded it, it added 0. So over here 10 and 0, what is the maximum? So maximum is 10, so this will return 10. Okay, and over here 10 plus 0, and over here 10 plus 0, so this is 10 plus 0, and this is 20, so 20 and 0, so 20 and 0, 20 and 10, so 20 and 10, what is the maximum? Maximum is 20, so this will return 20. Okay, now 20 over here we have 30, so 20 plus 30, so this basically would return 30 plus 20, which is 50. Okay, similarly this is 10, 10, 20, over here what will get? 10, 10, so this is 10, 10 plus 0, 10, 20 and 10, what is maximum? 20 is maximum. Okay, 20, no, sorry, over here we got 10, right? So 20 plus 10, so this is 30, so 20, this over here will get 30. Okay, 30, and so this return 10, so this basically we got 10. Over here 10 and 20, we got 30, so 30 and 10. Okay, so 30 and 10, if we do maximum what will get? 30 will get. Okay, so now what we got? So 30 we got, 50 we got, so basically 50, maximum of 50 and 30 if we do, then what will be the result? So it will be 50 only, so 50 is the answer. Okay, 50 we can see in our eyes also, like 30 and 20 if we pick, so it will be the maximum profit we can gain. Okay, now if you can see over here, so we are calculating subproblems, so we have overlapping subproblems. So for example, f of 0 1 we are calculating over here, f of 0 1 over here also. Why erasure is coming? F of 0 1 is over here also. F of 0 0 is over here, f of 0 0 is over here. Okay, f of 1 1 is over here, f of 1 1 is over here. Okay, so we have overlapping subproblems, and when we have overlapping subproblems, then what we can do? So we can optimize with dynamic programming, so we can memoize the value, or we can go for the tabulation. Okay, so two approaches we can take. So one is top down and another is bottom up. So this is memoization and this is tabulation. Okay, all right, so now we have understood the problem, so let's try to convert this into a code. Okay, so over here we can take two parameters, index and to denote the item, and to have the capacity, the remaining capacity. Okay, so and we will have two cases, so exclude case and include case. Okay, exclude case and include case. So exclude case, what we are doing, so we are going for the next item f of index minus 1, and weight capacity would have remained same. Okay, when you are including, now while including we have to check like whether whenever we are including whether we can include or not, because the item we are picking, so that should be having lesser weight than the lesser or same weight with the available capacity. Okay, so over here we can, so we have to initially we can declare a 0, include 0, but we can check like whether the current weight of the current item is less than or equal to the available capacity. So then only you can take, so in that case it would be include is equal to, so it will add value, right? So it will add value, so value would be the current index, the value of the current item, and then we look forward for the next item. Then what will do, it will be index minus 1 capacity, but capacity would be decreased because capacity will be decreased because we need to subtract the current weight as well. So what was the weight? It was weight of the current item. Okay, so this is done. Okay, now finally what you have to do, so finally you have to return maximum of include and exclude. Okay, so maximum include and exclude. Now we have to write the base cases also, right? So over here if index is equal to 0, then what you have to check, so we have to check like whether the 0th item value is lesser than or equal to the current available capacity. So in that case, if weight of the 0th item is less than or equal to the current available capacity, then we can simply return the value of the 0th item. Okay, else we'll return 0, because if it does not satisfy, so if it does not satisfy, then we'll return 0. Okay, so now what will be the edge cases? So edge cases can be like either we don't have the items, so either we don't have the items, so like length of the items is 0, so you can say n is equal to 0 if we are denoting, or we can say capacity can be 0 also. Okay, so if you are having capacity 0, or like we are having no items, so then we can simply return 0. Okay, so that are the edge cases that we can handle in our code. Okay, now what will be the time complexity? So time complexity would be 2 to the power n, because we have two choices, either we can include or exclude. Okay, space complexity would be O of n, because you are using auxiliary stack space over here, so this is O of 2 to the power n, and space complexity O of n. Okay, now let's try to code this up and then we'll optimize over there only. Okay, first we'll declare a variable n to get the length of the items, to get the number of items. Okay, now we can initially check the edge cases. So if n is equal to 0, or capacity is 0, then you can return 0. Okay, this is fine. Okay, then we can declare a function to get the maximum profit. Okay, and it will accept two parameters, index and capacity. Okay, now we'll write the base case later. Let's handle two cases, exclude and include case. Exclude, if you are excluding, then what we are doing, so we are going for the next item without including the current item, so it will be index minus 1 and capacity would remain same over here. And when we are including, then initially we are declaring as 0, because you have to check whether we can include or not, and if weight of the current item is less than is equal to the current available capacity, then only we can include. So in that case, include would be current, will need to include the current value, okay, current value of the item, plus we need to go for the next item. So simply copy this capacity, and we need to subtract the capacity over here, so it will be weight of the current index, okay. And then finally we can return maximum of include and exclude. So this would be include and exclude, okay. Okay, so this is done. Now over here we can see, we can check one more cases, like if capacity becomes 0 anytime. So if capacity becomes 0, then you can simply return 0. So this is one of the best case, okay. Another case would be if we reached index 0, then index 0, then what we have to check, we have to check that 0th item has weight of the 0th item has the available less than or equal to the available capacity. So if it is lesser, I have not added if over here. So if it is lesser, then only we can return the current value, okay. So return the current value over here, 0th item value. And if it does not satisfy, right, if you cannot include the 0th item, then what will do, will it return 0 only, because we are not unable to pick the 0th item, so it will not add any value, okay. So now finally what we can do over here, so we can call this function get maximum profit. So get maximum profit, we will call this, index would be n-1, capacity we can pass the existing capacity, okay. Let's check any spelling mistake over here. Capacity return 0, if capacity 0 return 0, weight less than equal to capacity return value 0, return 0. Would get maximum profit, include 0, index added 0, return maximum of include exclude, and get maximum profit. We forget the return statement over here, return, okay. So and if we execute this, then obviously it will run, okay. Now we can optimize this using 2D DP table, but to save the time I am using the LRU cache over here, okay. From functools import LRU cache, okay. And so over here we'll declare add LRU cache, max size to none, okay. So this is basically we are doing the top down DP, we are basically memoizing the value, okay. Top down memoization with recursion, okay. Now what will be now let's try to run this again. If we submit this, okay, still it's failing. I mean, in other platform it works, but over here it's failing. It's fine. I mean, then we can do what we can do. We can comment out this code, okay, and move for tabulation. So what we can do, okay. So now over here we will declare a DP table. So DP, so we'll go for tabulation. So we need a table 0 star n, okay, for underscore in. What will be the range would be capacity plus 1. So this should be capacity plus 1, okay, capacity plus 1, and this should be range n, okay. hope it is fine. Capacity plus 1, because we need to go till the available capacity, right? So capacity plus 1 for underscore range n. Okay, so this is n. Okay, now okay, so now what we have added over here, what base case we have added over here, this is we added. Okay, so we can say for w in range, so basically wt0, let me write the code, then I will tell you. wt0 and capacity plus 1. Okay, so over here what we have done, so basically what we have said over here, if index is 0, so then means we are considering the 0th item. Okay, now for the 0th item, if it is under the capacity, so if it is within the limit, right, the available capacity, then you can include, right? So if it is, so let's say we have capacity 8, okay, and the current 0th item weight is 2, then we can include. If it is 3, we can include. If it is 4, we can include. If it is 5, we can include. So till the available capacity we can include. Okay, and what it will add the values, it will add the value of its own, like the 0th. So we have, it will be the 0th item's value. Okay, so in this case we can simply do like dp of 0 weight is equal to value of 0. Okay, so this is done. Okay, now we need to check, we need to run 2 loops because we have 2 indexes over here. So for index in range n, so for what will be the index, so currently we will be running till 1 0 we have already covered, index 0 we have covered, now we have to run from 1 to n. Okay, then what you have to do, we have to check for the capacity. So for w in range 0 to capacity plus 1. Okay, it will run till capacity. Okay, so 2 loops we have defined over here. Now we will first include the exclude case. Exclude would be dp of index minus 1, and over here it will be w. Okay, include would be 0, and then what you have to do, we have to check the available capacity. So weight of index less than is equal to current available weight. Okay, and then we can include val of the current index plus dp of index minus 1. Okay, so previous items value, previous rows value plus we need to add d, so this will be capacity. So capacity is currently w minus weight of the current index. Okay, so for I in range, for index in range, exclude include, over here it is done. Okay, now what you have to do, we have to assign the value in the current row. So it will be index of w is equal to maximum of include exclude. Okay, so index is done, then okay, so this is index w max over here. leaving any cases over here. DP of index. Okay, I think we are good. Let's check. Then we can return dp of n minus 1 and then capacity. Okay. Hope we are good. Let's try to run this. Awesome. Okay, so now let's try to submit this. Awesome. Cool. So for the, I forgot to mention the time complexity for the previous approach. So we would have the time complexity of O of n square after optimization. Space complexity would be O of n square because of the iterative cache or 2D repeatable if you are using, and auxiliary stack space. For auxiliary stack space we will have space complexity of O of n. Over here, what will be the time complexity? So time complexity would be O of n square. It will remain same because you are running 2 loops. Okay. Space complexity would be O of n square. Okay. And we will not have any auxiliary stack space. Okay. Now can we still improve this solution? Okay. I think we can space optimize this. Okay. Okay, so let's declare our usual approach, previous and current. So previous should be, so let's try to copy the same code and write separately. So this should be over here. Okay, now over here it will be previous. So remove this one. Current would be over here. Okay, so previous and current. Now why we can space optimize this, because you can see over here we are just referring the previous row's value, and previous row's value we are including in the current row. So dp of index, to calculate the dp of index you are referring the value from the previous row only, right? So if we keep the previous row value, then we can optimize this, right? So in this case, so that's why you have taken two 1D array over here. So previous and current. Okay, now this dp of 0 would be, it will be initial row. So previous, this will be previous. dp of index minus 1, this would be previous. dp of index minus 1, this would be previous. Okay. dp of index would be current. Okay, and finally we can return we can return previous of capacity. Okay, so hope everything is good. Previous of w, this is current of w is equal to, forgot to switch. Okay, so previous would be current. Okay, so previous would be current. So once you are out of the inner loop, okay, it's passing as well. Let's try to submit this. So now the time complexity remains same. So for this, time complexity still remains same, O of n square. O of n square. Space complexity is O of 2n, or you can say O of n. Okay, because we have used two 1D arrays over here. Sorry, it will be O of w or capacity. O of w or capacity. Okay, 2w or capacity. So we are using two 1D arrays, right? Okay, now I think we can still improve this. Okay, so we can still space optimize this. Okay, so you can see over here, so we are referring only the previous row. So I mean, if you are referring only the previous row value to calculate the current row, do we still need to maintain two 1D array? I think no, right? We can still have the one array, and that will suffice. Okay, so in that case, what we can say, so we'll remove this. Okay, let it remain same. We are calculating the value. Okay, now over here what we'll do, okay, so let's check this out. So we are doing value of index plus previous of weight minus the capacity minus the weight of the index. Okay, so if you are from left to right, if you are from moving from left to right, so let's say we are calculating the previous of 5. Okay, so previous of 5, let's say previous of 5. Okay, now that we have already calculated over here. Okay, so this inner loop might have already calculated, but we have to refer the previous row value. We don't have to refer the current row value, right? So this inner loop is running, right? So this if might have updated the value, so that if we keep from left to right, then this can be error prone, right? This can be error prone, so this may not give the actual result, so this may refer the current row's value, right? So in this case, what you can do, we can start from right to left. So if we do from right to left, then the previous row's value, in the previous row's value will remain same. So we can still refer the previous row's value, because we are switching over here, right? So current becomes previous becomes current, right? So in this case, what we can say, so rather than starting from left to right, we can reverse it. Okay, we can reverse it. Okay, so this will be reversed. It will start from right to left. Okay, now this current is no more required, because we are referring only the 1D array, so previous over here, and this is also not required, so you can comment out this one. Okay, and finally what we have, so we have then over here return previous capacity, and now if we try to execute this, hope it will run. Awesome. All right, so it also ran as well. Okay, so I mean, you can see like like this part, I mean this part was understanding. I mean for me also it took a while to understand actually. Okay, so I was referring couple of articles. Okay, so then I found out like, okay, this is the trick over here. Okay, it's not invented by me. Okay, so trust me. Okay, okay, that's all. Thank you.